Welcome to this presentation. In this model, let us have an insight of Unit 1 of Antenna on Microwave Engineering. Unit 1 deals with the following topics. It is microwave frequency bands, physical concept of radiation, near and far field regions, field and power radiated by an antenna, antenna pattern characteristics, antenna gain and efficiency, aperture efficiency and effective area, antenna noise temperature and G by T, impedance matching, Frisk transmission equation, link budget and link margin, and noise characterization of microwave receiver. So at the end of this session, the student will be able to apply the basic principles and evaluate the antenna parameters and link power budgets. Now let us discuss about the microwave frequency bands. Microwaves are a form of the electromagnetic radiation with wavelengths ranging from about 1 meter to 1 millimeter with frequencies between 300 MHz to 300 GHz. Different sources of different frequency ranges as microwaves, and the above broad definition includes both UHF and the EHF bands. So this diagram shows the spectrum and where the microwave ranges from 300 MHz to 300 GHz. This table shows the different electromagnetic spectrum with their wavelength and frequency and photon energy. So as I said earlier, the microwave ranges, its wavelength ranges from 1 millimeter to 1 meter, and its frequency ranges from 300 MHz to 300 GHz. And the photon energy lies between 1.24 millielectron volt to 1.24 microelectron volt. These are the various microwave frequency bands, whereas the L band ranges from 1 to 2 GHz and its wavelength is 15 meter to 30 centimeter, and S band frequency ranges from 2 to 4 GHz and its wavelength ranges from 7.5 centimeter to 15 centimeter, and so on. And we can also see the various applications of these bands. For example, the Ku band is particularly used in satellite communication, and K band in radar and satellite communications, and so on. So this table shows the entire band. And now let us see the physical concept of radiation. The world of antennas encompasses the understanding of the meaning, purpose, parameters, and types of antennas. It also spells the theoretical and practical aspects of antennas and their selection criterion for specific applications and range of operation. An antenna area is considered as a region of transition between a transmission line and space. Antennas radiate, couple, concentrate, or direct electromagnetic energy in the desired and assigned direction. An antenna may be isotropic or anisotropic. There is no hard and fast rule for selecting an antenna for a particular frequency range of application. While choosing an antenna, many electrical, mechanical, and structural aspects are to be taken into account. These aspects include radiation pattern, gain, efficiency, impedance, frequency characteristics, shape, size, weight, and look of the antennas, and above all, their economic viability. In some applications like radars and mobiles, the same antenna may be used for transmission and reception, while in others, radio and television transmission and reception of signals require separate antennas which differ in shape and size and other characteristics. In principle, there is no difference in selection factors relating to transmitting and receiving antennas. The cost, shape, size, etc. make the main difference. Still, high efficiency and high gain are the basic requirements for transmitting antennas, whereas low side lobes and large signal noise ratio are the key selection criteria for the receiving antennas. Antennas may vary in size for the order of few millimeters, strip antennas in cellular phones, to thousands of feet, dish antennas for astronomical observations. Besides, 1D linear arrays and 2D planar arrays with length of diameters of tens of kilometers operate at the lower edge of the frequency spectrum. So a radio antenna may be defined as a structure associated with a region of transition between a guided wave and a free space wave. Antennas convert electron to photon or vice versa. Regardless of antenna type, all involve the same basic principle that radiation is produced by accelerated or deaccelerated charge. The basic equation of radiation may be expressed as IL is equal to QV. So this is the basic radiation equation. When electric charges undergo acceleration or deceleration, electromagnetic radiation will be produced. Hence, the motion of charges, that is currents, is the source of radiation. Here, not all current distribution will produce a strong enough radiation for communication. So, to create radiation, there must be a time varying current or di by dt or an acceleration or deceleration. If the charge is not moving, a current is not created and there is no radiation. If the charge is moving with a uniform velocity, there is no radiation if the wire is straight, and infinite in extent if there is radiation if the wire is curved, bent, discontinuous, terminated, or truncated. So if the charge is oscillating in a time motion, it radiates even if the wire is straight. The time changing current or accelerated charges radiates. This is the main principle. And the equation that as IL is equal to QV, I is the time changing current and L is the length of current element and Q is the charge, and small v is the time change of velocity, which equals the acceleration of the charge. For steady state harmonic variation, we usually focus on current. For transient pulses, we focus on charge, and the radiation is perpendicular to the acceleration, and the radiated power is proportional to the square of IL or QV, right? So the two-wire transmission line as shown in this figure is connected to a radio frequency generator, a transmitter. Along the uniform part of the line, energy is guided as a plane transverse electromagnetic mode, that is TEM wave, with little loss. The spacing between wires is assumed to be a small fraction of the wavelength. Further on, the transmission line opens out a tapered transition. As the separation approaches the order of the wavelength or more, the wave tends to be radiated so that the opened out line acts like an antenna which launches a free space wave. The current on the transmission line float on the antenna and end there, but the fields associated with them keep on going. The study of transmission lines reveals that there would be perfect reflection of a wave if it is open circuited or short circuited. In fact, reflections are present even if there is a slight mismatch on account of terminations or imperfections in the transmission path itself. An equivalent circuit of line with the loss can be drawn in terms of resistance or inductance L and capacitance C, or only in terms of L and C for a lossless line. The burden of carrying energy, that is contents of a propagating wave, is shared by electric and magnetic fields or voltage and current alike. The portions of energy shared by each are accounted by the well-known relations, that is CV squared by 2 for electric field and Li squared by 2 for magnetic wave. Right. Consider a wave propagating down a line finding an open circuited end. As a wave arrives at the OC end, the current becomes zero and part of the energy shared by the magnetic field becomes zero. But since the energy can neither be created or not destroyed, the only way out is that this burden is also taken up by the surviving field, that is electric field. So in the expression CV squared by 2, the line parameter C cannot change unless the area of cross section A. The separation D or the permittivity of the material occupying the space in the line configuration gets altered. The change of voltage is the only possibility by which the additional energy can be carried by the electric field. Thus, the voltage rises at the OC end and to enable it to carry the total energy. The voltage at a point of the OC is now higher than just before a little distance toward its sending end. Now, the current starts flowing back, which amounts to traveling of the current wave towards the sending end. And the voltage wave joins the rays as it was earlier, but this time both waves are the reflected ones and share their own burdens as before. In fact, the current momentarily remains zero and the two only at the OC point. Similarly, if the line at the if the line is short circuited at the receiving end, the voltage becomes zero and part of energy shared by it is momentarily shared by the magnetic field. This time the current rises at the receiving end, resulting in initiation of a voltage wave followed by a current wave as we can see now. So it is the current distribution, right, one second. So it is the current distribution on the antennas that produce the radiation. Usually these current distributions are excited by the transmission lines and waveguides. In cases of a perfect open circuits or perfect short circuits, theoretically there must be perfect reflection. Since the wave possesses a moment of inertia like property, it will take some time to change its direction. However, smaller this time may be, and some energy is likely to leak into the space. This process of leakage can be termed as radiation. This phenomenon is better understood through the example of open-circuited parallel line. The more is the opening at the end of the line, the more time will be taken by the wave to change its direction, and thus more energy will leak into the space, or there will be more coupling of transmission line into the space. So the maximum radiation will therefore occur when two wires at the end are flat to form a 180-degree angle. And the transmitting antenna, this is a region of a transition from a guided wave or a transmission line to a free space wave. So the receiving antenna is a region of transition from a space wave to guided wave and a transmission line. Thus, an antenna is a transition device or transducer between guided wave and a free space wave, or vice versa. The antenna is a device which interfaces a circuit and space. From the circuit point of view, the antennas appear to be the transmission lines as a resistance, or are called radiation resistance. It is not related to any resistance in the antenna itself, but it is a resistance coupled from the space to the antenna terminals. So in the transmitting case, the radiated power is absorbed by objects at a distance, that is tree, buildings on the ground, sky and other antennas. In the receiving case, the passive radiation from distant objects or active radiation from other antennas rises an apparent temperature of RR. For lossless antennas, this temperature has nothing to do with the physical temperature of the antenna itself, but is related to the temperature of the distant objects that the antenna is looking at. In this case, in a sense, a receiving antenna may be regarded as a remote sensing temperature measuring device. So the radiation resistance RR may be thought of as a virtual resistance that doesn't exist physically, but as a quantity of the coupling the antenna to distant regions of space via a virtual transmission line. So, and for a transmission, now let us see the principle. Under time-varying condition, Maxwell's equations predict the radiation of EM energy from the current source. And while transmission lines are designed to minimize this radiation loss, and radiation into free space become main purpose in the case of antennas. For steady-state harmonic variations, usually we focus on time-changing current. For transients or pulses, we focus on accelerated charge, and the radiation is perpendicular to the acceleration. The radiated power is proportional to the square of IL or QV, as I said earlier. So, as a transmitting antenna, the transmission line is connected to source at a generator at one end. Along the uniform part of the line, energy is guided as a plane TM wave with a little loss. Spacing between line a small fraction of lambda. As the line is opened out and the separation between the two lines becomes comparable to lambda. It acts like an antenna and launches a free space wave, and since the currents on the transmission line flow out of the antenna, but fields associated with them keep on going. From the circuit point of view, the antennas appear to be the lines of resistance as R0, that is called radiation resistance as said earlier. So this is the physical concept of radiation. So as a receiving antenna, active radiation or by other antennas and passive radiation from distant objects rises the apparent temperature of RR. This has nothing to do with the physical temperature of the antenna itself, but it is related to the temperature of the distant objects that the antenna is looking at. RR may be thought of as a virtual resistance that doesn't exist physically, but is quantity coupling of the antenna to distant regions of space via a virtual transmission line. So this diagram shows the concept of radiation in the receiving mode. Thank you.